I think we can get started. 5:02, I think we'll get started. If anyone wants to join in, we'll let them in. Well, I appreciate everyone hopping on again tonight. Thanks for joining us last week. We'll have this class, and I think we have one more on Thursday. First and foremost, I guess I'll ask, are there any questions from last Thursday's class? Second question, did everyone send Cam the homework that was assigned?
Yeah.
Of course, there was no homework, so I'm just checking to make sure everyone was listening. Appreciate it. Yeah, we'll kind of continue the conversation around protective relay applications and really the approach to testing. We talk a lot about the power system, transmission system, all the elements of the system, the protection and the controls and the relaying, at a high level, conceptual level, fundamental level, application level, but there's another layer, and all of this stuff has to be designed, engineered, built, tested, and commissioned. And testing and commissioning is one of the most important phases, if not the most important phase, because you have to get it right. There's no 95% out of 100. The testing has to be right. And the test personnel need to understand the design intent to be able to capture and identify any issues or any misapplications or design errors. So there's a lot to go into the testing. It may seem simple to just walk up, hook up a test set, and test and make sure you get a green check mark in your test software, but there's a lot more to it. As you've probably learned last week, and you'll learn a little more today and on Thursday. So just a quick reminder, you'll have Cam as well as myself. We don't need to go through our intros again. We have that from last week, so we're going to move right into the content here. So we're going to continue talking a little bit about relay isolation and preparation. We'll get into some of safety and HPI, and we'll talk about testing setup and connections, and look at what all of those things mean. Jumping into the isolation, who remembers what this was called from last week? How about Jeremy? Does Jeremy remember?
So like a PT switch?
Close.
P something.
One letter off. Shane, something to add?
Is it a FT switch?
FT, there you go. What does FT stand for? Anyone? It stands for flexi test. And that is an ABB specific test switch name, or Westinghouse if you were in the olden days. So, but they're often all variations and manufacturers of these types of test switches, whether it's States, ABB, GE, they often are commonly referred to as FT switches, even though that's only specific to ABB. But anyways, yeah, so FT switch, flexi test switch. And what is the purpose of these switches? Or Robert?
I'm not entirely sure. We had a homework question with this a while back, but yep. I wasn't here last week. My apologies.
Oh, well, that's good. All right, so one of your classmates can have. How about Nate?
Wait, sorry, could you repeat the question?
This test switch, this FT test switch, what is it used for?
Will you save the video?
Is it for just like testing, like inputting?
Well, I have problem with the hearing. I just, I wanted to see the video and a transcription by my, by my vision. Otherwise, I can't hear. That's why the problem. I appreciate if you save the video.
We're saving this one.
Okay, thank you.
Yep. So I'm sorry, Nate. Can you repeat what you said?
Would this just be like where you would test outputs from relays, or like just checking for like internal stuff?
Yeah, a combo of both. So these test switches offer isolation points for inputs and outputs to protective relays, right? So it gives you a point of disconnection or isolation, whether it could be an input or for a logic input, it could be an output that does a tripping function. It could be voltages and currents, right? Because the relays need voltages and currents in order to make decisions, right? That's what they're looking at. The relays are really looking at voltages and currents and the relationship between them to make decisions, right? That's ultimately what the relays are for. And depending on the application, they look at a series of whatever impedance or overcurrent or voltage or whatever. It depends on the relay. We talked about distance relays last time. So what allows us to do is isolate the relay, but yeah, we can also use this as a test block. We can insert a test paddle. We can connect our relay test sets up to it. And on the bottom is where the field connections are. On the top, typically, I've seen it the other way around, which is not great, but typically on the top is where the relay side is. So you plug your test set in, a test paddle into that top, and then you can use the screw connections on that paddle to connect to your relays. So then you can do the testing. We talked a lot about isolation last week. Why do we care? Why do we want to isolate relays?
I think I remember this part. It's so that we can keep workers safe. If you're isolating like higher voltages and utilizing this, it's a lot safer.
Mm-hmm. Safety is paramount, number one priority, absolutely. There's another reason. Does anyone recall what that reason is? Think about the one line that we had up on the screen, and we had a Bangor line and a Boston line, and we were trying to isolate the three relays that were associated with that one line. But we didn't want to affect any of the other power system, the other line or the transformer, right? So we write up these procedures, we establish the procedures, and we go through our due diligence to make sure that we are only isolating the things that we are working on, and we are fully isolated, and we don't have any impact on the things that need to remain in service. So we write up those procedures to make sure we don't disturb the things that need to remain, basically, and we only truly isolate the things that are inside our zone of clearance or our work zone, because we do not want to have misoperations. We do not want to trip off things if they're in service. So we got to be mindful of that. So we spend a lot of time looking at the drawings, looking at the I/O diagrams, writing up those procedures. I think I mentioned last week that it probably will take longer to write up a procedure, an isolation procedure, and have someone check it and go through that QA/QC process than it would be to actually isolate, test, a relay. But that's what it takes. Because we live in a CYA world, we want to make sure A, we keep everybody safe, 100%. B, we don't want to trip off something or cause a misoperation. We don't know if what's hanging. Well, we should know and probably would understand what's hanging off that transformer or that bus, whether it's a hospital, an airport, could be residence, right? It could be a whole industrial complex, warehouse, Amazon data center. We don't know, but the reality is, we don't want to disrupt that power, basically. So we spend a lot of time writing up those procedures and then using these test switches to isolate. So, all right. Any questions on that so far? And fantastic. So digging down a little further, let's see if I can go back. As I mentioned earlier, we've got some of these things that isolate outputs. Maybe there's inputs, there's currents, and there's voltages. So what what procedure or what sequence of operations should we consider as we isolate this? Do we just isolate that test switch from left to right? Or do we isolate voltages first and output second? I think you got the answer on the screen, but what would make the most sense? If a relay is making a decision based on currents and voltages and the relationship between them, what might you isolate before you isolate voltages and currents? Let me rephrase it. If I opened a test switch for a volt phase A voltage that the relay now no longer sees phase A voltage, it goes to 0. What might that simulate?
Might trip a breaker by mistake.
Undervolted. Oh, yeah, lost.
So if you have a fault on a phase of a transmission line, what happens to the voltage? If you have a ground fault on a transmission line. Generally, the voltage collapse, right? So the voltage would collapse, go towards 0. The current is going to spike. So if I went up to a relay and opened up a voltage first, relays are smart enough probably to realize it's not a fault, but in the older relays, not the case. It could actually look like it would lose a voltage, and it could, now you've got an impedance measurement, it could fall within the zone of protection, and it could trip. So that's why voltages are last on that. We used to call it voltage restraint in the old days, testing old relays, because it was actually the voltages that would physically restrain the inductive devices that were in the old electromechanical relays. So it's good, the best to leave that for last. So generally, the order of operation would be critical outputs. So that would be tripping breakers, the breaker fail initiate stuff, anything that trips a lockout, right? And then your other outputs, because again, the relay is making decisions based on currents, voltages, and inputs, actually. So all of those things kind of drive the logic to those outputs. So if you think about a logic diagram, all your outputs are on the right-hand side, all your inputs are on the left-hand side, and all your logic's in the middle, right? If you look at it from left to right. So you start from right to left, essentially, to go through your isolation of those test switches. So get your outputs done so you're not worried about causing any trips. If you do open a current or voltage, right, your communication-based tripping, you could isolate your fiber optics, or you could turn off a switch that would disable a protection scheme. Any inputs, it could be breaker A fingers, it could be anything that's wired in. Again, inputs are part of the logic diagram too. Voltages, currents, and an input or a series of inputs in any and or combination also drive logic. So it's important to open that stuff in this order of operation. Questions on that? We had someone that dropped off and came back. Did you get him, Cam? Good.
Yep.
Okay. All right. So we did talk about safety. Another big common term you'll hear in the field is human performance improvement. We're all humans. Humans make mistakes. It's in our nature. Nobody's perfect. Nobody ever will be perfect. Right? So we have a lot of these tools. Again, isolation procedures are one. We talk about all of these things to make sure that we eliminate to the greatest extent possible any potential for making a mistake or causing an error. We find all these error likely situations. Could be someone that isn't proficient in relay testing, doesn't understand schemes. It could be somebody's tired, someone's coming back from vacation, someone's sick, somebody's got something going on at home. There's all sorts of things that can play into and could cause these error likely situations. So we have a lot of tools that we use out in the field to help us work through those things, because there's no such thing as a perfect scenario, and no such thing as a perfect human, right? So some of these tools, pre-job briefing, that's basically your safety brief, project planning, some of those isolation procedures that we talked about, stop and collaborate. If you get to a point where you're feeling unsure, you have a peer with you, you stop, you collaborate, Phonetic alphabet is a good way to use transfer information along with three-way communication. I'm not going to get into a significant detail about what each one of these things are, but flagging, putting up barriers, signage, tape, anything that can draw your attention to the equipment you're working on or barricade you away from things you're not supposed to use. So these are all tools that can help you. And the four core tools on the left-hand side, your questioning attitude, your conservative decision-making, your effective communication, and stopping when unsure. Those four mindset tools, if you will, sort of drive those, we'll call them, I don't know, physical tools, I guess is the best term for them. But it really is a mindset. We do talk a lot about just getting to the work, but there's a lot to that to get you to a safe spot to do the work and perform it successfully. As I mentioned last week, setting yourselves up for success. So any questions on these HPI tools? We teach a whole class on HPI. It is a 2-day class. I can't talk about it in 3 minutes and give you the impact, but we can give you some of these pocket guides next time we come up and visit, so you can see what we mean by what these tools are. The description of each of these things in these pocket guides. If we can't get up there, we'll send you some. Any questions on this? And again, HPI, it's not just to do with the safety of being safe, it's with respect to doing anything. If you're doing something, you can make a mistake, right? Engineering, driving a car, mowing the lawn, you name it. And of course, if we're talking about testing, we're talking about field work, most importantly, we'll take a moment to talk about PPE. What does PPE stand for?
Personal protective equipment.
There you go. Anybody have or do any work that requires special PPE?
Yeah. We have steel toes, eyeglasses, and hard hats where I work.
Yep. Yeah, and again, we're out in the field with these relays. Are all in substations or cubicles, switchgear, etc. So you're prone to voltage, high voltage, arc flash. So at a minimum, your Z87 rated PPE safety glasses, appropriately arc flash and FR rated clothing, long sleeve, or natural fibers, but generally FR is required mandatory. Rated gloves, and it's also important to understand that there's a couple different types of ratings for gloves. There's voltage rated gloves and there's arc rated gloves, and they aren't necessarily the same. An arc rated glove will give you arc flash protection, but it may not offer shock protection. A voltage rated glove may have an arc rating. So you got to be mindful of, if you're just putting on some mechanics gloves that have an arc rating, you could still potentially get a shock hazard there. So something to consider as if you start to do some of this kind of work. And again, rated footwear, rated soles, safety toes. Some clients are actually going to a composite toe because they don't want, again, any steel or anything in the electrical world. I know steel have a higher crush resistance. So it would depend, again, in making sure you understand what you're working in and what PPE is applicable to your specific needs. Any questions on PPE? All right. Finally, let's talk about some tests. Oh, go ahead.
What would be the safety devices for high voltage?
So high voltage safety devices?
Yeah, I mean, working with high voltage, what kind of safety devices need to have?
Yeah, I mean, high voltage, you got similar PPE, of course. You would have a higher voltage rated glove. Generally, you'd have rubber gloves. You might have leather insulators to go over it. You have long fiberglass, what they call shotgun sticks, or some way of keeping you separated from the high voltage. There's a whole different set of rules that go along with high voltage, and especially with respect to what the actual voltage is. If it's 13.8 kV, or if it's 230 kV, or 500 kV, 765 kV. So there's a lot of other specifics that go along with that. There's at 765 to some of those upper voltages, there's not a lot of protection at those voltages. But there's a lot of specialized people have a lot of specialized training, what they're called competent and qualified workers that are allowed to work on those things. So for testing relays, we're going to work at the control voltage level, 125 volt DC generally, 120 volt AC, and everything's less than 250 volts. So you're going to work in a yard where there's high voltage, but you're not going to generally be up near what that high voltage is.
Do we need to wear specific shoes in high voltage?
Yeah, well, you're going to wear your EH rated. There's an EH rated sole. You look at the tag of a work boot or whatever, and it'll have an EH rating, which is designed for electrical hazard. Working in electrical environments.
Yeah, thank you.
Yeah, you're welcome. Great questions. What are we testing? All right, so we've got a relay. It's connected to voltages. It's connected to currents. It's connected to outputs. It's got some inputs. There's all the stuff outside the box, and there's all the stuff inside the box. So we want to test everything that we can to validate that the relay sees what it needs to. So at the end of the day, what we're hired to do, or when we're going to be testing this stuff, we want to make sure if that relay sees an abnormal system condition, it's going to operate the way that the design engineer and relay settings engineer intended it to operate. So we're going to simulate those tests. We're going to make sure, remember I said, it looks at voltages and currents and makes decisions based on those. So we would want to make sure that we're looking at the metering quantities. So we're going to inject voltages and currents into the relay. And we're going to make sure that the PT ratios, CT ratios match what are shown on the drawings. So if we put in 5 amp secondary and the relay is set for a 2000 to 5 amp CT ratio, what should I see as primary amps in the relay? Or what would the relay see? We have a 2000 to 5 CT ratio that's connected to the relay, and we put 5 amps into the relay. What would the relay think it's seeing from a primary perspective?
2000.
2000. There you go. Right. So we verify that. If we're expecting 2000 to 5, the drawings say 2000 to 5, and we put 5 amps in and we see 3000 amps, we have a problem. Right. So that's the kind of stuff we're looking at. Same with voltage. If it's 600 to 1 ratio, 1000 to 1 ratio, maybe it's hooked up phase to phase and not phase to neutral. So we're checking those things. So we check metering first to make sure, because remember, all the settings of a relay are going to be based on primary values through the CT and PT ratios, basically. So if we don't have that information in the relay correct right out of the gate, we're going to have a lot of problems downstream with all the other relay settings, because they're all based on primary amps, right? That's what the studies are going to be done in. So we double check that right out of the gate. And if there could be, maybe there's a physical problem, maybe there's a wiring problem. So we want to check those things. And we want to check all the elemental pickups. We talked about distance relaying last week. Well, there's the Mohs circles. We want to make sure that everything is working inside the circle and doesn't work outside the circle, the impedance related settings. Overcurrents, voltages, they're going to have set points. You're going to have an instantaneous overcurrent of 16 amps or whatever the application calls for. We want to make sure it picks up after 16 amps and not before. Voltage under, over, all of the things that are set. And you would have to go through and make sure you're checking all those relay settings to ensure you're figuring out what's actually turned on. All right, torque controllers. What's torque control? You guys talk about that at all? Basically, we'll call it internal permission. So you set up some of these equations that say you want this function or this element only to work for certain, maybe it's a range of an angle, or maybe it's there's a piece of logic that's in there that's only work when this function's enabled. Those sorts of things. So those are kind of another a logic. Timers. So there's so much involved, and I'm not getting deep into those relay settings, but it's important that we validate each one of those settings that's enabled. Same with inputs, outputs. Once you verify the elements, now your inputs and outputs, you're going to make sure that those work. If you turn on an input with DC, you want to see that it turns on and the relay sees it. You want to see an output works when you toggle that output. And then you want to take those inputs and those outputs and make sure, as I mentioned before, you're looking at your logic diagrams. You turn on your inputs, your logic, you test your bits of logic, your ands, your ors, your nors, your whatever, your nots, and then make sure you get the right outputs. And in this case, we're talking about physical outputs, not just gated outputs. A gated output could become, or your logic equation could drive a physical output. And protection logic, which we just kind of talked about, that's all the decision making, all that Boolean logic, right? And I mentioned too last week we talked about truth tables. Some of this logic could have dozens of inputs and outputs feeding other inputs, and all these logical chains. And we want to make sure that when we test this stuff, it operates when it's supposed to, when all the combinations are correct, and then it doesn't when it's not correct, when they're not aligned. And then another part of this is the display. And again, a display point is just another piece of the logic, making sure that what is on the front screen, you get a chance to test and make sure that that's all what the engineer wanted you to see. And there's push buttons in many relays. Some are settable, some are not. There's LEDs, there's all sorts of indications. So that's another piece of what needs to be tested. So what questions do you have on that? So who can tell me how a relay works?
It's taking some voltage and current and making decisions based on logic.
What else does it use?
Statuses.
Yep. So you've got inputs, could be inputs into the relay, logical, digital inputs, right? You've got analog inputs, which are your voltages and your currents. And all of those combinations, for the most part, it's really looking at voltages and currents because that's what it's seeing. That's how it's seeing the system, right? The power system element that it's protecting. It's monitoring those voltages and those currents via CTs and PTs or CCVTs, some sort of voltage transformer or current transformer, right, to transform it down to a usable signal. And it looks at those things and looks for an abnormal condition. And yes, then there's inputs, digital inputs that could help drive some of those decisions as well. So when it makes a decision, what happens? If it determines,
closer.
Go ahead, say again.
Very closer.
Well, it could, yeah. But it's going to, depending on the abnormal system condition or the system condition that it sees, it's going to make a decision, and it's going to either operate an output, or it's going to operate some sort of logical output bit. It could send communications. It could close a physical output, right? All of that stuff. So that's really it in a nutshell. So that's kind of what we're testing. A couple things to consider. So if we're sitting, have you all connected up to, say, an SEL relay with a accelerator software or or GE relay or anything like that?
We did a little bit in the lab.
Yeah.
Yep, there's a lab.
Okay. Okay. So you have some familiarity with that connective process. So I won't spend a lot of time on that. But when you sit down as the test engineer, you're going to sit in front of that relay after you've got it all isolated and you've done all your due diligence, right? And you're going to connect to that relay with your communication cable or your Ethernet cable or whatever. And the very first thing you're going to do is you're going to save a copy of the settings that are sitting in that relay as you found them. And you're going to tuck those away somewhere, because if this was an in-service relay and it had settings that were in there that you need to make sure if you accidentally change those and you have no record of those and we need to put them back, and this is experience talking, and I've seen it happen where someone went to a relay, they made changes to the relay, it caused a trip, because it was a Cooper relay or something, and instead of read and send settings, it was upload download, and upload download can mean two different things depending on where it's referring to, whether it's the relay or whether it's the computer that you're connecting into, and it was opposite of what your instinct or your intuition would say. So instead of reading settings, they sent default settings, which resulted in a lower current pickup. And once those settings got loaded and the relay got saved, it determined an overcurrent and tripped. Now, the problem with that is they didn't have the settings to put back in the relay. So there was a big scramble. But anyways, long story short, make sure you understand first and foremost that you understand the nomenclature being used, whether it's read, write, send, open, GE, I can't remember what GE uses, SEL uses read and send, I believe. Cooper obviously was upload, download, but it's important to understand that. And having that set of settings and tucked away, first you can use it for reference, but if you need to, for any reason, have a record of what was found there, and if you ever have to put it back in for an emergency purpose, you have a copy of it. Any event reports that are in the relay, just in case there was some event report that was triggered from an actual system fault that perhaps the client didn't get a chance to download, it's great to save those. This sequential events recorder, you can copy that data out as well. So what you're trying to do is establish a baseline. This is how I sat down and found this relay. So you're basically covering yourself to say, I've saved these things, I have these things, this is how I found it. And you can either restore it, but you also have a record of what was there. What question?
Brian, one thing I want to add, if you don't mind.
Sure.
For the SER that he was just talking about, the sequential event recorder, that command is actually going to be used primarily during your relay testing. So if you can save a copy of whatever was in the relay prior to initiating your testing, that would be really good, just to provide to the client that this is what we found prior to doing any of our work, because
Right.
the SER is going to be basically utilized during your whole testing process to evaluate the outputs, trigger any of the inputs, any of the protective relay elements that the relay is going to be initiating with the new settings that are going to be involved. So just an FYI.
Does everyone understand what SER is, or what a sequential events recorder is in an SEL relay?
I think I get it. One question is it time stamped?
Yeah.
Okay.
Yep. Correct. So an event report in an SEL relay generally is an event report that has a series of information from an actual trigger event. If there was a fault on a system, it will log pre-fault time, your currents, voltages, digital inputs, whatever, and it puts it all in one big event report file. Sometimes you see them as CEV files, some of them you hear ComTrade, right? So it's an actual event file all wrapped up. The SER data is sort of a line by line text-based, if you will. GE is a little different because you got to use their human, their little graphic interface on their software. But it's an element. It's a bit, a relay word bit, bit by bit with a timestamp. So, whether input 101 turned on or output 101 closed, or whether it established the 3PT for three-pole trip, whatever happens to be set in that SCR, it will be in a line by line and in order of how it operated as far as the relay saw it, usually out to the millisecond. So that becomes very valuable, well, in fault analysis, right? As well as in relay testing, because sometimes when you have to put all that logic together and test all that logic, you got to figure out what comes in before the other thing. What was the actual initiating event for that output, to make sure that was the right thing. So it's a very useful tool. And as Cam said, you use it a lot during the testing, and so you don't want to lose any important information from actual system operation. So that's why we copy it out. Same with the event reports. So here's a front panel. Go ahead.
I was curious, if you have relays communicating within each other or to each other within perhaps the same zone, and this might sound stupid, but if they're communicating and one sees the other one tripped off, can your SCR collect the data that's occurring at that relay that wasn't affected but might have a transient in the system? Does that make sense?
So the SCR in each relay?
Yes. Like if they're communicating with one another and it sees, oh, this one tripped off, or send an output to trip or something.
Right.
I guess just so you can monitor what happens throughout the whole system.
Yep.
Not just that is that something that happens, or?
So in a fault analysis, if it came to an actual analysis need, yeah, I could interrogate other adjacent, we'll call them system relays. So if I have a line fault on one line and I also want to get the SCR data from a adjacent line that didn't trip, yeah, I can log in and get that data, and I'm going to see probably some disturbances or some other thing that though that relay didn't trip, it's going to see some abnormal conditions. It might. And you can use that as a tool to help evaluate and determine, if you have to study again and analyze a fault. They aren't going to communicate with each other. They're not going to send each other fault information or SCR information. But a lot of times, any relay that's connected to your system, especially the close ones, they might see some of those system conditions. They're just not programmed to trip for those specific conditions because that's not the element they're protecting. But yeah, you can use the other SCRs, and you may need to. Sometimes the information isn't necessarily available, and you have to go on a sort of an investigative hunt. And again, these SCRs are only programmed by people. The engineers put what they want for these elements, these relay word bits and logic, whatever they want. They put what they need or think they need in the SCR to monitor. But if they forget something, because again, they're human, right? It's good to have other relays. So it's possible. Yeah.
Thank you.
You're welcome. Great question. Any other questions? We'll get a little bit to that in the end-to-end testing one on Thursday, I think. That's a little bit different scenario because you've got two relays, they have a pilot channel between them. They're communicating to each other, looking at a line, and we're doing some synchronized testing. And we will use the SCR data from both ends to make sure that they're doing what they're supposed to be doing, especially in a blocking scheme or permissive scheme where you want to put a fault that's not on the line, right? One relay is going to see if it's forward looking, but it's going to be beyond the other relay. Both relays are still going to see it, but one's going to say, no, it's behind me, don't trip, to the other guy. So we use that information as we get through the end-to-end testing. So it becomes very valuable at that point, especially to the millisecond, because we want to evaluate, in a power system, milliseconds matter, right? Most of this stuff we want to trip off in a cycle, 2 cycles, and that's how many milliseconds is a cycle? That's a question. Who has the answer?
Like 16.67 or something.
There you go. 16 milliseconds is a long time in a power system, especially in fault conditions. So we do that end-to-end testing, and we've got communication channels and some latencies and all that stuff. We want to make sure we validate that information. So that's where the SCR, from a testing perspective, gets very important. And in the case and scenario like you just mentioned, one relay had a trip, one maybe didn't trip, we would look at that, next relay out to see if it saw it, if it was in a direction behind it, or if it was, somewhere else. So it becomes very important. So on this here slide, I think we've got, this is a front panel of what? I think this is a 411L, SCL 421 maybe. 411L because it's an 87L. It's kind of 87L channel there. So, but again, a part of the testing, yes, we have voltages, we have currents, we have hardwired digital inputs, statuses, etc., hardwired outputs. But what can we consider these push buttons and these lights? Can we consider those push buttons an input and those lights an output? Yeah, and logic, for sure. So this is another part. All right, so this is another, it's just display points and LEDs and whatever, but it's absolutely important because this is now your interface. And this is what someone's going to walk up to and see. They're going to use it for some local control. They're going to use it for local indication. And this is generally the first place someone goes if there actually is a fault. They're going to look for these targets. That's what this whole lower left-hand column, 2 columns are basically targets. So we validate those as well. And again, those LEDs and those push buttons in that big logic diagram, that's all they are, is inputs and outputs. And their settings associated with what their functionality is. A lot of times this comes through with the default labels, but SEL actually has customizable, configurable labels that you can print out and create. And it's important to make sure you're validating and verifying that it has the right labels in there as well. Because the relay engineer could have made changes to those targets and those push buttons and the LEDs associated with the push buttons. So it's always a good question to ask. And you'll notice it as you get through the logic and review that if it aligns or not. Most of the time, from what I've seen, they usually customize them. So there's the last question there. Do you know where to find SEL templates? If you had to go find some place to get these templates to create your own labels, where do you think you could go to find those?
The SEL website.
SEL website. Pretty easy question, pretty easy answer. But of course, you'd validate and verify with the relay engineer. A lot of times, the relays ship with books, and they actually have some printable templates already, some blank ones in with the book. But more and more clients are opting not. Now buying a book or instruction manual to go along with the relay is actually an added cost, whereas it used to be a part of the relay cost. So may not always be there. So these are some similar connections. Now we're getting ready to prepare for testing. Right now we're going to make some physical connections. If we have to use, we may not have everything through a test switch. We may have to use some of the terminals on the backs of relays, et cetera. Obviously, we've got to be mindful of voltages and being smart with that. But these are some of the different kinds of test block terminals that we might encounter. Simple terminals with screws. We've got these little green, what I call Phoenix connectors, which are sort of a compression type connector. The relay panel there on the lower right hand, that looks like an SCL relay. So again, more of the screw type terminals. SCL does offer another type of connection called a connectorized plug, which is actually, it just plugs into the back of the relay. It's kind of a hybrid. It's not a green plug like that. It's a lot more robust. CMP used those for quite a while. I think they've gone away from them now. But you could really just unplug those and plug in another a test lead to directly into the back. So it was almost kind of like those screw terminals didn't exist. Instead, there's wires on them, and you could just take that whole black plug in or out. Of course, to work on this stuff, you're going to need some screwdrivers, probably insulated would be a good idea. You'll need a multimeter, and a holding screwdriver works handy too, because a lot of times, well, most of the time, and it should be this way, for any of these screw terminals, they should be ring lugs, not forks. If they're forks, my suggestion would be to replace them, because that means they could, fall out very easily or get pulled out with any type of pressure. Even though there's a good, screw clamping force there, I've seen them pull out pretty easily. So you might need a little mini insulated screwdriver for these green Phoenix blocks, because those are actually pretty small. You see those more on maybe communications with their smaller gauge, 22, 24 gauge wire. A lot of time on the relay connections, you're number 10, number 12, number 14 gauge. Most of the time in some of these bigger power type terminals, you could get up to 8 gauge, but you're not really going to see much more than that on the back of a relay. All right, what types of tools do we need? You need some test leads, preferably fused safety leads. Why do we care? Well, there's a nice little picture of a burnt up test probe down there. So we want to make sure we're using the right tools, because voltages are there. That's why we wear the gloves. That's why we wear the PPE. I've physically been burnt by an arc flash. It's hot. That's all I can tell you is it's hot, very, very hot. So we got to be mindful of the equipment that you use. It's in good condition. You've got the barriers, like this little twist guard plug on the upper right hand side. You can see the black lead has it's retracted, and then the red lead has it pushed forward. So you don't touch those two leads together if you're too close to a plus or minus DC, for example. So very mindful of this. DC is pretty powerful. There's AC's got a zero crossing, DC does not. Right? DC has the battery inertia, I guess, whatever you want to call it, but that oomph from the battery and a very low resistant, high current in a short circuit situation. Have the States or some sort of test plug. This is a States one. They make similar ones. ABB makes them where they're top screw instead of the ends like this. I prefer the end screws, these end plugs, because you can plug into the back or the front, I guess, versus the top, because sometimes you have test switches mounted on top of each other, and they'll actually cause a problem where you can't get them plugged in. There's your, we'll use forks for testing applications, but not for hardwired. I'm not a fan of these alligator clips over here because they're metal, right? I would definitely probably not use those. I would make sure if I did use alligator clips, and I would only use an alligator clip in a last resort scenario, but they would have to have insulation on them. Color coding could mean something to you. You could have different colors of these: red, black, blue, white, green, orange, yellow, and sometimes you develop your own sort of color scheme as to what you want to hook up for your voltages, currents, DC, plus, minus, all of that. So what are other questions here? A good one is making sure your leads are rated for the currents you're going to use. Again, I've had folks run seen using current and applying current from a test set and letting it run, and it was 10 amps of current, but the relay, the lead was only rated, or the probe was only rated for 6 amps. So guess what happens? The probe melted, right? So it's paying attention to the ratings of your equipment. All right. And then, yeah, barriers. We talked about some HPI tools, physical tools. You can put barriers, you can put tape, electrical tape, dielectric, vinyl, something to help with avoiding, touching exposed parts, energized exposed parts, or just physical tags or barrier tape or something so that you can create your zone. Like, don't open this test switch, only open this one. Don't operate this switch, only operate this switch, work in this relay, that sort of stuff. All right. Well, here's a test set. This is a Doble 6150, and I'm going to kick it over to you, Cam, to take it on from here.
Yes, sir. All right, I got 20-ish minutes left. I'm going to slam through this
Sorry,
a little bit. It's all good. A lot of good information, Brian, which is much appreciated. But if anyone has any questions while I'm possibly rambling at any point, just yell at me. So like Brian was talking about, we've done our due diligence. We've looked at everything. This is probably the most common test set. This is probably the only one that I've really ever used when I was out in the field, was a Doble F6150. It's pretty common to see this out in the field to be utilizing for relay testing. What you can see on the red and blue ports are the current and voltage analog outputs that are basically going to be supplied from the test set to the relay when you're doing your testing to be able to supply current and voltage values to the relay. These are usually interchangeable. It's pretty common to obviously keep one side voltages, one side currents, vice versa. Your logic outputs, which is the green box right here, are what going to be picked up from the relay. So if you're monitoring an input or you're trying to see a specific element being picked up, this is what you'll be basically wiring in series to your test set to verify that the relay is operating the correct output or picking up the correct command properly. Kind of the same idea for the inputs. Again, it's more or less just seeing what the relay is monitoring, stuff like that. The battery simulator, this is where you'll be supplying the DC to the test set from where the DC source is connected to on the relay to monitor and make sure in the situation where, if there's a loss of DC to the relay, that type of command, the test set will be monitoring that as well. And then lastly, the communications port. These will be talked about a lot more Thursday when we're talking about end-to-end testing, but it's basically any of the communication parameters that will be dictated based on usually specifically like a line relaying scheme where a relay is talking to another relay, possibly at another substation across the line. It could be within the substation as well, depending on the scenario. Basically stuff like that. Before you even connect any of your current or voltages, obviously we're doing our due diligence to verify our connection parameters, verifying we're in the correct panel, the correct test switches, if applicable in this situation, and verifying we're mainly going to be in the same circuit as the CTs and voltages, like CCPTs or PTs that we're going to be connected to, or that the relay will be connected to when it goes in service. So verifying the correct configuration, your ratios are all correct. You're verifying those with the settings or the design engineer's intent towards your testing purposes, all that stuff. This is what basically your connections will look like once you're all set up. One thing I'd like to mention is, like Brian was talking about before, the color coordination is usually pretty important because by the time you're probably halfway through the test, I would guess, would be my experience. You're going to have a lot of cables coming out of this test set. If they're just all random colors, they're going to be intertwined. It's all in this little section on the relay cabinet, so it's going to be tough to verify what's going where or making sure that you're connected correctly from the test set to the relay. So like he said, color coordinating's usually pretty important. I like to do red, white, and blue usually in the field for phases A, B, and C on the currents and the potentials. You can switch it up however you need to, but basically the finished view is going to be your currents going into the correct inputs on the relay, your voltage is going into the correct inputs on the relay, verifying your outputs by wiring in a spare output from the relay to your logic input to make sure that the test set sees that the output picks up when need be, and which I'll get into in a couple slides here. And this is kind of one of the big things. Can anybody tell me what would be an issue based on specifically the test switch on the schematic in the top right and how the test switch is configured on the bottom right? We talked about it last week where we had these paddles that we basically just throw right into the knife switches so that they directly supply currents and voltages straight up to the relay. Well, if you were to do that in this situation based on the schematic, and if it was physically wired per the schematic, what would happen? Basically be supplying voltage to everything but the relay on the rest of the circuit, which could end up having a couple scenarios. Number one, somebody could be working on that circuit, and adjacent to. So somebody else, like an electrician's in another panel that could be paralleled to this circuit, they get zapped with the test set voltage. Could be supplying secondary voltage back up to a PT. That creates a lot of issues, not even necessarily safety issues, but could damage the equipment, whatever it may be.
Let's dig into this just a little bit further, Kim, just so that we're clear. If you look at the test switch, the way it shows in the schematic, that AC schematic, you've got test 2CD, TS1, and the blades are A, B, C, and J. A, B, C, that's the first two blades on that test switch below. J is the far right blade. And if you look at the physical blades or physical test knife blades, test switches, whatever for each of that, right? They open with the hinge is down. So you see that hinge is down, which is equates to that little hinge up on the schematic, right? And that would be terminals 2, 4, 6, and 20, which is correct because the bottom terminals on that FT are the evens and the top terminals are the odd numbers. So it goes 1, 2, top, bottom, 3, 4, top, bottom, all the way to the right. So what I mentioned a little earlier with the test switch, the test switch only fits in the top of that, the test plug on the left would slide into those test ports on the top of that FT switch with all those blades are open, right? But that's going to actually put the test set plugged into those odd numbers, which is looking out into the field, not the relay. We want it to look into the relay. So what Cam's pointing out is that test switch is basically hooked up backwards.
Mm-hmm.
Right, something to worry about. I've seen this in service before like this, and it's you got to be very careful because you think you have an isolated relay, but you're actually plugging into a live voltage, live DC, live whatever. Or to Cam's point, if it's de-energized and you accidentally turn a test set on and put some currents and voltages in there, maybe somebody else is using, working on that circuit downstream. They think it's isolated and it's not.
Mm-hmm.
So anybody have questions on what this is illustrating? Excellent.
I guess one last point to that too, Brian, is a lot of the times, these relays could be bench tested, meaning that they do their relay testing without them actually being placed into the cabinet. So they're wiring all their voltages and currents in directly to the back of the relay rather than plugging into these test switches that would be in the panel in this situation. So again, if that's the case, you got to make sure you're doing your due diligence during your functional testing when you're actually wired in, everything's connected to the relay and whatnot, and verifying that your isolation parameters, in this case the knife switches, are in the correct polarity. verifying that all the terminals are connected to the proper termination points, to the correct devices, etc. It's a, it could be a situation where you're in a weird, not super correlated step-by-step process, and you're kind of scattered all over the place. But there's these overlapping elements that you need to make sure that you're aware of once you're out there, and verifying that this equipment will functionally operate correctly when it's placed in service. So, yeah, a lot of important stuff when you're out there. But continuing on, one of the things that we do to verify the relay's functionality based on the settings is we end up usually connecting a spare output from the relay, something that's not connected to terminal blocks, if we can. Something that's usually just labeled as spare in the relay settings. That's what we end up plugging into for the logic input to basically change the parameters of that output. In this case, for the example here, it would be out 213. We'd basically be changing the output parameters to verify testing points. So if you're testing a certain element, you'd place that element within out 213 so that the output would operate when it needs to. Again, it's all based on what you're testing at the time, but that's usually how we do it to verify it. And again, this is what we would be pulling for the SER data to supply to the client in this case. As it mentions over here, connecting to a terminal block or the relay, I personally would prefer connecting straight to the relay. That way you don't have any outside contingencies that could apply. Again, you're going off the design intent. Let's say it's connected to a terminal block. That doesn't necessarily mean that the terminal block doesn't go anywhere else. You may be wiring to that, reconfiguring the output to basically close in when you're doing your testing. It could for some reason be connected to some other correlating device and another panel or somewhere else around the control house, which could lead to issues. So it's better safe than sorry just to always connect to a spare unwired output in this case. And it may be polarity sensitive too, depending on the situation. So it's always stuff to keep out for. The biggest thing, usually when you're out in the field starting relay testing and you go to your lead engineer, you always say, all right, what do I do? How do I set up this test plan? I would say probably 9 times out of 10, depending on the situation you're in, your lead will look at you and say, did you download the instruction manual to that relay? And probably you're going to say, yes, I did, or no, I didn't. Either way, they're going to say, yep, just look at the manual. It's going to be
nice to me when they say that. I can tell you
no,
that.
no.
More colorful.
Yes.
Terminology.
Yep, for sure. The instruction manual is going to be your best friend and your worst nightmare when you're out in the field, because it's going to have every answer you need, but it's going to be the worst way to ever find the answers. Nice thing about nowadays, you can Control F in a PDF on your laptop to kind of navigate the manual a lot easier, to find certain commands or certain elements that you need to learn about a little bit more, or figure out how you're going to pick up or how you're going to test. But realistically, this is going to be your best source of information to determine the equations you need to pick up elements, do your testing, test your logic diagrams based on the design intent, and review the specs as well. So it's a blessing and a curse, that's for sure. Looking in the manual as well, you're going to be able to dictate what the limits of the relay are. Going back to Brian's point earlier when he was talking about, burning up test plugs and whatnot. It's one thing to burn up a test plug in the field. That costs a couple cents. It's another to burn up the relay itself when you're doing your testing. That costs thousands of dollars. That goes directly back to the client, who will be extremely unhappy to find out that would happen. So testing your elements is great. Understand the parameters of which currents or voltages necessarily need to be picked up at what time and what zone, et cetera, but understanding the absolute limits that the relay can handle or that should be monitoring during a fault scenario or anything like that in the aspects that you'll be testing, you got to understand those as well to make sure that you don't exceed those at any point, because some of those might get a little skewy, especially in certain situations.
Yeah, you could have a 5 amp nominal rated relay current input, but you might have a 45 amp instantaneous test point that you need to test. So that's 9 times what the nominal rating, continuous rating of the relay is. But you got to
Right.
figure out. Obviously, the relay is designed to see that for very short periods of time. That it's monitoring the system and it's going to see the same thing. But you got to make sure you set your tests up and your test leads to make sure they're capable of carrying that amount of current. But you're setting your tests up so that they're only there for a moment, very, very
Mhm.
small period of time, not continuous, because that's what will cause the burnup.
Yep. Absolutely.
Can I ask a question real quick?
Yeah, please do, Rob.
Yeah, you had said that you would connect to the spare output contacts to test earlier you had said that when you're running testing. Are you not concerned with the actual contacts that will be used when the relays finally set their performance?
That's a great question.
That's
So
fantastic.
in the event that you are testing, so for example, say that there is a predetermined output, say out 201, that's going to be tripping a breaker. That one we're going to be directly connecting to. The only reason we're connecting to a spare output is to measure specific elements that don't trigger a necessary output in that scenario, where you're trying to basically take a bit of information in the relay settings and monitor that element specifically, not a whole equation like a trip scenario where you have multiple different elements coming in and operating a specific contact. You're looking at just one little bit of information provided by the relay settings.
So here's an example. In a time overcurrent application, you have a pickup value and then you have a time test value, right? So the minimum pickup you would use a spare output for, say the minimum pickup is 1 amp. That's when the relay will start timing when it sees 1 amp and above. Then it uses the curve, the timing curve, and the time dial and the tap and all that stuff, or time dial. The tap is part of the minimum pickup, but that timed out element will be in the trip string. So we would want to monitor the trip string. So you understand the difference. The minimum pickup isn't going to operate an output that's going to trip a breaker or a device, because we want to make sure it trips based on the relay time curve, and the 51, we'll call it T element. That's going to be in the trip string. That's going to be in the output that's hardwired to trip a device. So we would make sure that that does trip that one. So that's the reason for the two different types of output testing. We don't want to go make changes to the logic and the hardwired output, the one that's actually do the tripping. We don't want to mess with that logic. We want to leave it alone. So we just keep changing the elements in the spare output for minimum pickup of overcurrent, minimum pickup of voltage, minimum, whatever, something along the way to help facilitate the testing. Does that make sense?
It does. Thank you.
Perfect. Going over the SER data again, as I previously mentioned to Brian, this is data that we'll export before we even start testing, have that as a backup to provide to the client in the event that, something happens, or like say a fault were to occur while we're doing our relay testing and that relay is out of service. We have the event recorded data previous to that to make sure that that relay doesn't communicate with anything else. We also utilize the SER command specifically in the situation where we provide data during testing so that we see specific elements pick up, time-stamped events taking place during our actual testing. And we usually save those and provide those with our test set results after our relay testing is complete. Let's see. Okay, so outputs from the relay, monitoring those in our test set. Like I said before, you're identifying your local isolation point, you're verifying that the output picks up when it needs to. How does it tie into other protective relays? Like say it's a breaker failure scenario where another relay would be issuing a breaker failure command to this relay. The trip command gets triggered based on that breaker failure initiate, and then vice versa, the breaker failure from this relay triggers a trip elsewhere. A lot of nitty gritty stuff that I could go into with these, but we're running low on time, so I'm going to continue. And then inputs, kind of the same idea. You're monitoring a specific event from another piece of equipment, whether it be a breaker status, whether the breaker is open or closed, whether a lockout gets rolled or not from a breaker failure situation or another event. And then as well as the relay inputs could be monitoring another relay. So usually easy example of this would be, one relay is monitoring another relay. That relay loses DC power completely. The relay gets shut off. That input will come in. So again, I could go into copious amounts of detail with these. If anyone has any specific questions regarding any of these, please speak up. Otherwise, I'm just gonna kind of keep going.
Yeah, I think the
Or
point.
I can end right here.
Right. The point is, looking at all the I/O, you want to make sure you're testing all of those things. From a relay perspective, you're testing from the test switch in, right? In that case, these are inputs. In the previous case, or test switch out for the outputs. Or no, I guess that would still be in, right? And we're using those test switches, and we're testing all of the used outputs and the logic associated with it. In some cases, you're going to have to set up a test plan or with your relay. For example, the breaker failure testing I mentioned last week. It uses status of the breaker, it uses current, and it uses a breaker fail initiate from an outside relay. And it has to have all of those things, and they have to operate within a certain amount of milliseconds. And that's a test that we would have to perform. So you'd have to hook up, relay output of the test set to the two inputs of the relay, and the output of the relay to an input of the test set, and set up a plan and make all that work, and then test the timing of it all and make sure it only works based on that breaker failure logic. So there's a lot of stuff. It could be alarms. It could be inputs could drive display points. They could drive LEDs. Maybe they're only used in an SCR, right? But all of those things have to be tested and documented. Because at the end of the day, what are we trying to accomplish? We're making sure that this relay, when it needs to, it sends an abnormal condition or some sort of control, it does what it's supposed to. When it needs to, and it doesn't do anything when it's not supposed to. And these relays have a lot of logic and settings built into them. And you need to be, understanding of the applications like we talked about last week. There's software that you can plug into these relays now and the test sets, and it'll automate testing for you, and it will manipulate settings and all that, which is great because it makes the test quick and probably can make test companies more profitable, but it's not truly testing the application as it's intended. It's manipulating the test. So I'm not a fan of that. But anyways, that's my soapbox moment. Thanks, Cam.
Any questions, guys?
Fantastic. Well, if you think about anything, let us know. I think Paul will send Paul the recording of this. Next week, we'll do a next class, which is Thursday. I think we get into end-to-end testing, right? Pilot scheme testing.
Yep. And then restoration processes too. So.
Well, we're going to focus mostly on the end-to-end stuff. If the restoration gets pushed out a little bit, I think there's going to be a lot more time better spent talking about the actual end-to-end testing. So we get the restoration great. Just the reverse of isolation, so to speak. All right, that's it for us. Any questions? Fantastic. Y'all have a great
Thanks, guys.
Okay.
Thanks, guys. Have a nice evening.
Thanks, guys. Have a good one.